Good morning. It's great to join you all today. It's an honor to be here. It's great to run into long-term colleagues in the hallways. I haven't seen so many people in these couple of years at times. I'd like to present a set of ideas today on work that I've been passionate about on the human side of AI systems in the open world. There's been a great deal of enthusiasm about AI and the technical side of machine learning, but there's been overall less work and success on the human-centered side of the reality of translating technologies into applications in different sectors. One of the directions in thinking about realistic uses of AI is to examine directions and ideas on how machines and people can work together in deeper ways. So today I'll discuss research on several pathways to achieving deeper human-AI teaming and synergy. I hope to stimulate enthusiasm about possibilities moving forward, and to reflect with you about where we stand on this front, in particular with the advent of an interesting disruption, the advent of capable large-scale language models. And I'd like to frame my presentation today with the inspirational ideas of an early contributor on work on human-computer interaction. This is Joseph Licklider. He was a computer scientist and a psychologist and a visionary who headed a DARPA computing office in the early 1960s. One of the earliest researchers, and it's interesting to read his history, to see one of the first real-time interactive systems in a day where computing was known to be batch. This computing system was named Whirlwind. It was a defense computer, but he was moved to see a real-time interacting computer for the first time, and it set his imagination going about possibilities, imagining a time like ours, but even more so, even in our future, where he wrote in a classic piece called Man-Computer Symbiosis, I'm sure he would have said human-computer in this day and age, people will set the goals, formulate the hypotheses, determine the criteria, and perform the evaluations. Computing machines will prepare the way for insights and decisions in technical and scientific thinking. And in that piece, he talks about this will require much tighter coupling between humans and machines, and creating a colleague whose competence supplements one's own. So I've been moved by and resonate with Licklider's vision. There's so much promise in developing AI as a tool for richly augmenting human reasoning, our abilities, our cognition, in a fluid, seamless way to support people while celebrating and respecting their primacy, their agency as central in defining goals, specifying directions, information needs, and supercharging and empowering people. Now, at the core of this vision is considering the capabilities and limitations of human intellect and the powers of machine intelligence to bolster human intellect in an on-demand way, as well as within the flow of human activities. So there's been a great deal of interest and interesting work in human-AI collaboration. Today, I will not cover that work, but I'll just give you a sense for directions, and I'll cast the work to date and moving into the future in the context of recent developments with large-scale language models like GPT-4. So I'll be addressing how we can move forward with Licklider's dream in today's context, where we have methods and techniques coming via decades of work here on the left, with building, and in many ways, incrementally and methodically, from the point of view of the last 24 months, building incrementally and in sets of ideas and layers. These long-honed machine learning techniques in inference, representation, and in human-AI interaction have been moving along, but now we have the advent of a very fast-paced and disruptive technology with these large-scale language models, LLMs. They're coming with the scale of a scaling up transformer architecture, coupled with self-supervised learning, supercharged with unprecedented data and compute resources that are now showing surprising and unexpected capabilities. So no matter what your interest in theory or practice with data mining and machine learning, you've no doubt been grappling in one way or another with the disruptiveness of large-scale models while thinking about where we came from on the left. What does this all mean? Well, my sense is that we all have questions about steps moving forward with the integration of where we've come and where we've been going with the updates we're seeing in disruptiveness. These new models and their capabilities are surprising, yet they are now facts of life. They're part of the natural science in some ways of computing, and we need to understand and pursue syntheses and integration of the prior long-term innovative, but perhaps more conventional powers of machine learning with the newer disruptive capabilities that we're still learning about. So opportunities ahead include harnessing the LLMs for their new capabilities and perhaps to use them instead of the methods on the prior path on the left. Another is to identify limitations, but glimmers of possibility, and to pursue innovations at the foundations of the large foundation models, to extend them, to understand them better. Then there's the construction of integrative weaves of the methods being developed on the long-term trajectories in machine learning with the new rising capabilities via bespoke or custom-tailored integrations where a traditional method, for example, can call a large-scale language model as part of its operations. And finally, there's all the work going on with giving LLMs the ability to call tools, including Bayesian inference, graphical representations, statistical packages, Python libraries, moving forward. Now, before jumping back to human-AI synergy in a world of rising large-scale language models, let's go on a brief arc through recent history. It's just amazing to me how fast things have been moving. We're only into the, I've been counting, we're only into the 12th year of an inflection with AI, with neural models, and I've been seeing fast-paced developments moving from early surprises in speech, actually on my floor at Microsoft Research during a summer visit by Jeff Hinton, onto convolutional models in vision. But in just a few years, just amazing to see all the benchmarks that have been hit at the level of parity with humans. Now, just 10 years ago, we were celebrating the power of discriminative neural models and applications like image-based diagnosis in medicine, spanning dermatology, radiology, looking at flat film radiology. And then just over the last couple of years, the rise of powerful generative models that could do surprising things, very surprising to me. When DALL-E 2 from OpenAI became available just maybe 2 years ago, I explored visualizations as part of my reflection about a home project. I was putting in a large-scale solar array in a new home, and I was told I needed to heat my pool with different bladders, ugly heating pads. And I said, well, why can't I combine these two together? So show me solar cells affixed to solar heat collectors for heating a pool. I was amazed by the power of compositionality that these systems had to imagine something that had not been created before, water flowing through solar cells. How would that look? How would that work? Giving me the ideas about how to approach my home project. And then it's been stunning to see the generative models and methods like inpainting and diffusion being used in protein design. Quite stunning work here by the Baker Lab at the University of Washington, a team that we've been collaborating with. And today we're seeing new forms of multimodal models, such as LavaMed from Microsoft, doing fine-tuning with tens of millions of figure caption pairs mined from PubMed Central. I think the headline or the title of this paper was, "Doing this all in one day." So it's not all intractable. There's lots to be done with research with lighter weight computation. But the headline of the last few months has been what we're seeing with generative models with scale and big scale. Now here's the data center where GPT-4 was birthed. It's just west of Des Moines, Iowa. The data center itself stands among the top 5 supercomputers in the world, with nearly 300,000 CPU cores, more than 10,000 top-line GPUs, and 400 gigabits per second of network connectivity for each GPU server. Moving ahead with this kind of investment is based on both theory and practice. theory about the expectations with scale, we can see with large-scale models, as well as empirical evidence. So performance depends strongly on scale, weakly on model shape, and there's been quite a bit of work on scaling laws, looking at what we can expect with losses on particular metrics based on compute, data set size, and parameters. Now here's a prediction of the loss with next word prediction as a function of compute that supported reliable prediction of some aspects of the performance of GPT-4 based on smaller models trained with 1,000 to 10,000 times less compute. We see here basically loss on predicting next word, and in some ways, Microsoft knew what it was buying when it scaled up this model working with OpenAI very closely. Because we hit that point there on the next word prediction. Now with scaling on primary tasks like next word prediction is unusually accurate with these empirical laws, for example, it's really not possible to predict when models will start to show specific skills or become capable of specific tasks. But what we're seeing is with the compute to get to those lower word error recognition rates, interesting emergence, sometimes appearing quite abruptly versus a less resource-intensive version of a model. Wei et al. Shows some work looking at this idea of this nonlinearity that takes us off the smooth scaling laws into what we might call surprises. So now I've been personally so impressed with the capabilities of models that are built with simply the task of predicting the next word. Yet when pushed hard with backprop and gradient descent, we go beyond just this idea of creating these gigantic language models into building rich real-world representations, I would say, rich embeddings of concepts and the world. And I've been studying this because this is a surprising, I think, result in some ways. I've been impressed by the results of Abdu and Pavlik, who are looking at these representations. For example, in one study they showed on the right here, looking at embedding spaces for colors, people refer to, and the embedding space in BERT, a BERT-controlled context with color, versus a perceptual model with human data. And these embeddings look similar. So these systems there's evidence they're learning rich representations of the real world. Now moving on to some surprising capabilities of GPT-4, my team gained access to an earlier version of GPT-4 last August as part of doing early studies of safety and reliability as part of our responsible AI overview at Microsoft, what we do when we get a new disruptive technology. And while looking at the safety issues, we began to think through doing deep dives into surprising capabilities. For me, two words came to mind: phase transition versus GPT 3.5, that would soon become ChatGPT months later, the first version. And the second word was polymathic. These systems really seemed to be moving across multiple disciplines with ease, fluidly combining disparate areas, medicine and law and so on, different tasks. And we started studying different topics, and it led to this paper that we actually broached the phrase artificial general intelligence. My view of this is more general AI, but we're seeing glimmers of what's possible. And just to give you a sense of what we saw, and if you go to talk to psychologists about intelligence, they'll talk about abstraction, the ability to abstract general concepts from specific instances, to generalize capabilities to new situations, and notions of compositionality and synthesis, combining parts or elements to form meaningful wholes from constituent expressions, combining diverse information, creating new ideas, solving problems, multisensory integration, and so on. And we explored in examples in our paper different dimensions that you might say along those lines of core notions of intelligence coming from the psychology community, cognitive psychology community. For example, could we ask the system to create graphics incorporating letters and then describing what they've done and allowing dialogue about them? Data visualization tasks, and this is actually creating animated data visualizations. This is a freeze frame of one. Manipulating data sets and visualizing them. Drawing, just, can you draw something like a unicorn? And even tracking over time how the abilities were changing as GPT-4 was being incremented. And remarkably, vision. I started playing with ASCII images myself, just like I would create various ASCII images, and the system would be, I quote unquote, seeing. This was the output of what we call DV3, was the code name for GPT-4 in the day, back in August and September. And we have an example in our paper of this seeing, where we've removed all commented code, removed a horn from this unicorn, and asked the system to put the horn back. And the idea of a system looking at code, looking at graphics code and saying, I know where to put the horn, was pretty remarkable to us. Another remarkable finding that I'm very excited about is what we see in the new models with theory of mind. And this will have something to say about human-AI synergy. Theory of mind has been considered a grand challenge of AI. Science Robotics called this out in 2018. How do we get systems to understand intentions for education, for collaboration, to recognize emotion? How do we build systems that understand that in daily life, humans do a lot of coordination with understanding the beliefs of others, emotions, desires, intentions? A lot of this capability, in some ways, is not the kind of thing we study in KDD. It's kind of the dark matter that sits, I believe, in training resources, but it's so omnipresent that these models can learn about them. They've been studied in psychology. What does Alice believe? What does Bob think that Alice believes? Different kinds of interactions where people hide things and leave a room and ask, can someone figure out what's changed without looking? Studies with kids on theory of mind. And just in time for Thanksgiving, we did an example that appears in our paper. We've all, especially in the United States, had an uncle or aunt over who has different beliefs, and so there's tension in the room over Thanksgiving meal among people who love each other. In this case, we have a challenge here about, we show in the paper, a Democrat mom who likes to be organic and fears vaccines, kind of what the user here might think is a closed-minded Republican uncle, doesn't like vaccines, and asking GPT-4 what this poor young son might do in this case. And you can read this case in the paper, but it really captures this beautiful notion of how a system can facilitate engagement. And just a few months after GPT-4 shipped, Michael Kaczynski did a really beautiful study also discovering theory of mind may have spontaneously emerged in large language models. Now, our team also turned to professional competency exams, looking at benchmarks of various kinds. Given my background doing work in AI and medicine, I was curious how well the system might do on benchmarks, including USMLE exams. This is the competency exams you have to pass in medical school to go on to practicing medicine, with just simple querying. And this is, the blue shows GPT-4 with a very basic querying versus where Google was in a paper published 2 weeks ago in Nature in the beige, with very complicated 44 calls using experts and so on to craft their prompts. Also, we noticed during this fall intensive study of GPT-4, in medicine, unexpected capabilities. This is an example of a question in medicine that medical students have to take. A 28-year-old man comes to the office with an episode of blood in his urine, and it's multiple choice. You get lab results and so on. Now, besides the core performance, I was pretty amazed at the ability of this system, a language model just trained on next word, to do counterfactual reasoning. Can you change the history or lab results with as minimal changes as possible to change the answer, the right answer, to make acute kidney injury the best answer, and then list the changes? And have the system go in and change something and say, yep, I'm going to change it so that it makes a single answer into a rich, interactive educational session, or a single question into a rich educational interaction. And now we're talking to the National Board of Medical Examiners about how to change the way education works and testing works in medicine. Can you shift the labs even more to make acute kidney injury even more likely? Now the system changes lab levels and says, okay, now I got you. I'm going to raise the patient's urea nitrogen and creatinine, lower the eosinophils. It's not going to be a parasitic infection now. And then back to theory of mind. Why might the student have selected malacoplakia? What findings would have led the student down the wrong path? Share reflections on the reasoning that the student came up with. And to have a really beautiful answer that I talked to physicians about. What was the medical student thinking when he or she gave the wrong answer? Just to think deeply, and we'll be talking about this at the panel this afternoon, what this means for education. Now, this month, I and colleagues have a cover story we're very proud of on a computational inflection for scientific discovery, where we talk more broadly than just large language models of the form I'll be getting into in just a few minutes. But it frames some interesting work we did early on in the fall with exploring the abilities of GPT-4 in scientific reasoning. So in preparing for an executive presentation, I grabbed like yesterday's Nature magazine. I get Nature and Science, and I read both of these. I highly recommend doing this. These magazines weekly when they come in. A paper had just come out on wetland emission and atmospheric sink changes explain methane growth in 2020. Why did methane go up during the pandemic when there was less transportation? And it's an interesting study. I asked the system many interesting questions. I input the whole paper as context, and I said, what are the key weaknesses of the study? How can the work be strengthened? If we assume that the author's hypothesis is incorrect, what else is going on? How might these hypotheses, these alternate views of what's happening, be studied? Did the authors overlook one or more important, potentially relevant modeling methodologies or tools? Look at the methods and write out a set of procedures for the authors for a follow-on study that would employ a Bayesian hierarchical model for the atmospheric 3D inversion part of their study. And then what are some general follow-ons? And I'm not going to go through details. I had to grab just little pieces of paragraphs, but the system was not bashful in answering this question about weaknesses in this paper. So we see the new power of these new capabilities that Licklider might himself agree, if he was alive today, supplement human reasoning, even in their raw form. But how might we take these techniques forward? This brings us back to thinking deeply about the relationship of human intellect and machine intelligence, and back to what I said earlier. What's the synthesis we might do to directly use the LLM capabilities to pursue new innovations where they're weak, to build integrative weaves, and to extend LLMs with calls to tools like Bayesian hierarchical reasoning and modeling. So in the spirit of Licklider's dream, I'll share several directions on human-AI teaming in the context of modern machine learning, including what we're seeing in large language models. What comes to mind in where we are today, given the history, 20 to 30 years of more recent history of human-AI collaboration work, are these topics. How can we think deeply about the core substrate of probability and utility that's really not supported by large-scale language models? How do we coordinate human and AI initiative in working on problems together? How do we leverage the complementarity of people and machines? How do we build models of people in the world? These are all topics that have been explored in this space. Employ grounding processes that would bring people and machines to the same mutual understanding, and master designs for interaction of the form we're all pursuing now, including work on integrating these large-scale language models into Microsoft products, for example. I'll focus on just a quick subset moving forward of those topics, but I wanted to show you the bigger list because I love to talk about those other topics not being covered today in Q&A if there's interest. First, on the core substrate of probability and utility, it's really clear we need, for many things that we do, a clear normative semantics for inference, axioms of probability and utility, and to have probabilities to do expected value decision-making, normative approaches to taking action in the world. These capabilities are not yet available directly in the core LLM technology. So we're all used to, this is long-term KDD work, going from data sets to probability distributions, let's say in healthcare, areas that I've worked in, including readmissions management, taking 13 years of data from the EHR, the electronic health record, reasoning about readmissions, doing an ROC curve, or in this case a positive rate versus a false positive rate curve on readmissions of patients discharged within 30 days, building systems like Readmissions Manager, and then thinking deeply about decision-making, inferring decisions and actions, where we answer the question that might come up in a hospital: where should I operate on that ROC curve? And being able to take a specific disease condition like congestive heart failure and a utility model with parameters, and saying, in this hospital, with this model, we understand what the implications are for policy. We can run simulators, build visualizations, understand that if we have an $800 fee for an intervention that might keep patients out of the hospital, and it's 35% efficacious, what it would mean for reducing readmissions and cost. And we've been used to our traditional methods, our conventional methods, doing exploration and discovery. For example, in work with Jenna Weens here on predicting infections in the hospital, C. diff or MRSA or VRE, a tragic problem that leads to 1 in 20 hospital visit problems and 5% death as the top 10 cause of death in the United States. To understand what's going on, looking at feature sets, for example, framing studies in causality, understanding work in space and time, which is where we took this work when we did this work. Large-scale language models cannot help us with this, nor really hard, high-stakes decision problems like how do we address and complement physicians. We've done work in this space to make less medical errors, to address avoidable medical errors, the third most common cause of death in the United States today. How do we build safety systems, for example? Addressing, like I did with Dave Lee, a student of mine, on the failure to rescue problem. How do we complement physicians so that we don't have this tragic phrase happen with our family members: failure to rescue, missing an opportunity to save patients who die encountering a treatable complication. In this work, using distant supervision, you can build systems that will really figure out what was missed, for example, by physicians. But there are places where we can see the LLMs playing a role. Let's talk about coordinating human and AI initiative. With coordinating initiative, the idea is we imagine a dialogue with a smart system. It could be with actual speech or dialogue abstractly working on a problem together. I want to figure out how to coordinate the initiative. We have lots of initiative coordination happening with machines in the real world. Tesla drivers will know about simple coordination where the Tesla says, take over, I can't go further, or tell me if I should go through this red light or not, or the stop sign. Almost 25 years ago, our lab thought deeply about expected utility to drive contributions by AI systems versus humans working together by talking about what might be desired in an AI system or not desired, and the system could take an action or not, that two-way square, and then computing what's the expected value of the system taking action, given that the user would like that action, and plotting that as a function of the probability of desire here, and the expected utility of not taking an action when it could have been valuable if the user desired it. And then thinking about, hey, we can actually ask to ground the intentions. It's not as valuable as taking action directly when it's desired, and it's more costly than doing nothing. But we have a threshold as to when to ask in a particular region of this geometric space. We also can learn about ideal timing of when the help may be invited. These were core methods used back in the 90s. You can see from the agent here working to schedule my daily appointments based on calendar interactions, looking at the text of the calendar, using, in those days, some of the first feeds we had coming out of email to give us machine learned models to make predictions about desired intentions. And since then, we've explored in more sophisticated methods the use of these systems to control fast-paced dialogue among people, in this case, a setting where an agent is playing the role of a moderator in a fast-paced game as to when to talk, how to jump in versus stand back, taking into consideration the actual costs of generating language and the delays and so on. You needed to do this well to have a fluid conversation at fast pace. What about largely language models? Well, we typically are struggling to get probabilistic information. One area that we've explored is, given the cost of using GPUs and doing workloads, can we make an inexpensive call and then look at the log probs to reason about stopping versus going deeper? Or when should we defer to experts versus even trying to do expensive prompting? One thing we learned about GPT-4 in the context of medical exams and medical benchmarks is, we said, wow, the log probs coming out of the system are quite well calibrated. In fact, much more calibrated in some ways, look at the green line here, than GPT 3.5. To me, it's extremely exciting that large-scale language models might, we're not there yet, one day understand calibrated competence in their generations. This is a very limited context of medical workload or benchmark competency exam questions. What we can use for work in this space, we can use log props to guide whether or not for a whole benchmark, we want to pay the price, changing the threshold in the log probs of the answers coming out of the system to those, for example, multiple choice questions, pay the price of going to, let's say, 44 calls versus just stopping and taking the answer from a simple query, simple prompt, and discover, for example, in a decision theoretic way, hey, you know, cost benefit, we only lose 1% accuracy on the whole benchmark with an 80% reduction in cost. Now, I'm going to move to another bullet on that integrative arrow that I showed before about now bringing together mixed initiative interaction with a large-scale language function, Copilot, which I know many of you use. Copilot's been shown in several studies to reduce, increase the productivity in particular metrics by about 50% of developers and engineers. As you know, as you're doing your development work with Copilot turned on, let's say in Visual Studio, your work and your work to do comments and so on becomes prompts to give the system context for generating code. Now, in work with intern Hussein Mazinar and Microsoft researchers Gagan Bansal and Adam Forney, we looked carefully at what the mixed initiative interaction was like working with Copilot. And you see here on top here, a little graph here showing recommendations shown, accepted, later shown, rejected, shown, browsed, accepted. To study what people were doing with Copilot, we built an ontology of states in the session with the programmer. For example, thinking and verifying a suggestion, deferring thought for later after accepting a suggestion, waiting for a suggestion, editing written code, editing a suggestion, integrating it, for example, looking at documentation. And we can look at a specific session of a developer and understand it in terms of the semantics of the visitations among these states of a programmer's session. One thing that we found was, from Copilot telemetry from hundreds of users, is a significant amount of time is spent looking and deliberating about suggestions coming from Copilot. And many of these suggestions are just rejected. Someone just keeps, after they look and think, they keep on going with their own work, and writing their own functions, for example. Part of this work was working after development sessions and having people look at their video and annotate and building models to predict what was going on in these hidden states that weren't being seen directly through telemetry. You get a sense for, across participants, where time was being sent normalized to total session time for each of the participants. Thinking, verifying a suggestion is quite up there in terms of what people are doing in working with Copilot. So there's opportunity for a mix of initiatives. So going back to the 1990s work and thinking about how can we integrate core classic mixed initiative interaction work with modern large-scale language models, functions, and services, we can now think through and write down a utility function here, expectation to say what's the expected value of showing a recommendation if we have a probabilistic model giving us, built through supervised machine learning, the likelihood of it being accepted. I'm wanting to sort of do a cost benefit, including latencies of people having to wait, for example, for a suggestion. Writing down a decision threshold probability that would guide whether to suppress a suggestion from a really excited Copilot trying to show the user something that they might reject. And going back to a utility theoretic viewpoint, at the x-axis here is the probability of accepting that suggestion. And then building a system that can actually featureize the situation, the context, and the space. In this case, we had 535 users who code in Python, looking over almost 5,000 coding sessions, where a session is defined as a sequence of actions with at most 30 minutes between actions. Looking at about almost 1,700 hours of coding, 170,000 events being shown to users or developers, 33,000 being accepted, yielding an acceptance rate of Copilot suggestions of 21% or so. And then building a model, XGBoost worked the best. Isn't it good to hear an old-fashioned algorithm like XGBoost in this room in an LLM world? But now we're going to actually sort of take these features and run the system And to give you a sense for how it could work and enhance the lives of developers, if we select 20% of suggestions to hide based on our analysis, 97% of those selected would have been rejected, saving time and effort on looking at suggestions that probably would have just led to a time sink. I have to say that before I leave mixed initiative interaction, there's lots of interesting work going on, including at Microsoft Research. This is work by Dan Boas, Sean Andrus, and myself, published last year on a continual learning in your kitchen. Now, sorry to make anybody dizzy here. This is an egocentric view wearing HoloLens, and somebody, basically, this is Dan. He's basically working in an interactive way with the system CLIP.
That's an orange.
To help us to understand bounding boxes and labels. In this case, what you see here is once the user, in this case Dan, has told the system what it's seeing, the system can go back in video and go forward in video and use all that data in a 3D space to say, well, this is our more training points to understand that object better. It's another weave of the two, LLMs and classic work. And then I have aspirations. I've talked to my friends and colleagues, some at Johns Hopkins, about what we might do someday. It's not clear how large language models and more traditional methods will come together, but to recognize surgical states, which have been done already, and to think through what it would mean someday to have mixed initiative. And this is a video from a collaboration between Johns Hopkins and Children's Hospital in Washington, D.C., in the physical world of using mixed initiative in a complex repair known as an anastomosis repair, where there's perception and turn-taking going on, a dialogue with mixed initiative. I'm going to give you a sense for what I'm thinking about with deeper melds of humans and machines coming in the future. Let me talk now about leveraging the complementarity of people and machines. It's another direction, looking at the rich complementarity of people and machines, back to our human intellect and machine intelligence view. Now we want to use, over the years, we've been using learning and inference for complementarity. So thinking about like, well, what can the machine do and what can the human do, and how could they best complement one another? One example from about a year and a half ago is looking at complementarity to change the way we do machine learning to understand histology, the area of pathology. And so the idea here is we want to shape machine learning for complementarity with human beings. There was a metastatic breast cancer challenge. It's called the Chameleon Grand Challenge 6-7 years ago. At the time, with pathologists looking at a workload of sections of lymph node tissue to see if there's signs of metastatic breast cancer in the lymph node. At the time, the human pathologists were superior to the neural net model in the competition. They had an error of 3.4%. But if you combine the AI and expert together, even in a simple way, you brought down the error, false positives, false negatives, to 0.5%, an 85% reduction in errors. And we thought, this is Brian Wilder, who was an intern with us at the time, and Ajay Kumar, we could do better than this. And so we spent the summer and into the fall working on how do you consider human expertise in DNN, we used to call them DNNs, not LLMs, they were smaller deep neural models. How can we basically optimize them to understand the value of human input by looking at the probability that the system, the neural model would have about what's going on in the cells, the probability with human input, and human input alone. And actually really looking at the value of information from a human being as part of the optimization. So if this is traditional machine learning, we want to minimize a loss function. But if we have a human performance data set in parallel, we can then say, let's see, here's the AI solo, here's AI plus human expertise. Let's build into the whole optimization loop the expected value of human input and do a joint model that includes, as part of the optimization, the output of a policy for when to ask a human. Now, when you do this, you can read about this online, how we did this work. We found the following. In the traditional machine learning, 70% of human errors were concentrated in a region containing just 10% of the cases. Standard machine learning failed in 30% of the region where humans were failing. When we did the joint optimization, there was 0% failure of the machine learned model in those human error regions. So here's a graphical view of this. Here's all cases. Here's the place where human beings are making errors in that little region. If you just train an AI model with ML, there's an intersection there where both the machine and the human are failing. With the joint optimization, you're literally pushing the model away from the human errors into a space where humans understand that can be queried reliably. This gets me so excited about what we can do with human AI complementarity and machinery for helping us build systems that work well with people. And there's more formal work in this space on teamwork, on joint execution, on leveraging human and machine intelligence in large-scale crowdsourcing that brings computer vision and humans together. Another area of complementarity is, which I think is really a rich opportunity for us in this community, is thinking about human cognition directly, building data sets, understanding mechanisms, and thinking about where do people have, in general, blind spots and gaps and biases. There's 100 years of cognitive psychology research that is yet to be harvested by our community to understand how to build machine systems that can complement humans to augment their intellect. And work we've done in our lab and other places on memory, attention, judgment, these core areas of cog-psych. Just as an example in memory, I find myself over the years promising too much in daily life. This was kind of a corny headline that appeared a few years ago. I guess someone called me a top scientist. But you know, I didn't like the fact that I would say, oh, I'll get you the abstract for the talk at KDD and the title. I think some of you just saw the title this morning. And then I get reminded on like Thursday, you promised me that title, where is it? And this led to a project. It was actually codenamed Einstein Project at Microsoft Research a few years ago. Could we understand email communications and pull out commitments that people make to each other or questions they have to each other, commitments to someone, commitments from someone, and build a system that could remind them about something they would likely forget, and then build a loop that could learn from, you know, let's say, an enterprise setting, users using the system, for example, to know that, to be reminded in a briefing mail, I'll do my best to add comments by the deadline, we'll send them back at the hotel, I'll send you a separate invite, to not get in, to keep my commitments and so on. And this system has been used by tens of millions of people now across the world. That's a really interesting area. So in the complementarity area, here are 4 areas on the other side of the LLM integration chart that I showed that I want to think deeply about with this community and others. How do we add extended memory into these large-scale language models that would let us do some of these things for capturing preferences to be complementary, especially with a general model? How do we capture experiences, failures, and successes? How do we understand, for a user, preferred context-sensitive methods and tools for systems calling tools? And how do we fine-tune these systems with data on human cognition, for example, that might not have been in the training data set, to build systems like large-scale language models that actually have some of the abilities we found we could build with more traditional methods? We have a standing question, for example. Can we replace the whole end-to-end neural modeling system we built for the commitments and requests system that's now part of a system being used across the world with a large-scale language model that would say, we could say, hey, what things might I forget? Figure it out. I'm suspicious that we can't do that very well. Now, on another front, we have to consider how we work with these systems to do what's called, in the linguistics community, and also in the human-AI collaboration world, grounding to achieve mutual understanding. Herb Clark and Susan Brennan, both colleagues over the years, define grounding as a joint activity, it could be with language or with watching or both, to coordinate on content and process, establishing and harnessing mutual knowledge, beliefs, and assumptions in communication about a task or an idea. So I have a dream sequence I put together here on an aspiration. Here's a human with a task at hand, driving with agency and primacy what needs to be done, communicating with an AI system which might not understand what he wants, but there's a back and forth. And finally, there's an understanding and a clear confirmation we're on the same page. And then thinking about where this would go when it comes to mixed initiative, to break down this problem into sub-problems, a machine saying, I can solve beta, but I can't touch alpha, that's for you to do, and then grounding on the mixed initiative part of who does what on sub-problems. Well, are these large-scale language models today good at grounding? I've been pretty impressed, especially recently in playing with Code Interpreter. I'm not sure how many people have been trying that out since July. But a recent study at Stanford by Omar Sheikh, Christina Gligoric, and Dan Jurasky on several workloads, comparing what humans do, one's an educational workload, for example, one's a mental health workload, how humans do to ground, to ask questions. What do you mean? Doing repairs, that's not what I meant, and so on, compared with the ability of GPT-4, GPT 3.5. What are their findings? Well, it sounds like, what they found is instruction following optimization seems to optimize for only single-turn conversations. It ignores the richer dimension of what humans do with each other in mixed initiative interaction as they ground. People are more strategic with grounding. People pursue multi-turn grounding. The LLM was biased towards immediate assumptions of common ground and moving on, often getting distracted by the prior, myopically, the prior turn, and asking clarification questions when it did, unrelated to the main task. There's work to be done on grounding, and I see really interesting efforts on the part of possibilities on the part of psychologists, linguists, AI researchers, KDD, ML experts, and so on this question of how can we take these systems forward to make them better at grounding. So getting to the top of the hour, I wanted to just give you a sense today of some topics. I had a bigger list to show, but I said I'm not going to fit that into an hour. Maybe we could do it in Q&A, of thinking deeply about bringing human and machine intellect together, thinking deeply about where we are with this LLM disruption, but thinking positively about how we can bring these worlds together with these discoveries that we've had and the surprises we've seen capabilities just over the last year and more to come. I have a wish list I put together. I'm not going to go through my wish list right now, but I've been talking to colleagues about what I want to see when it comes to going back to Licklider's 1960 charge to build a colleague whose competence supplements our own and figuring out how to have tighter coupling between humans and machines. I'll stop there. Thank you.